Okay, let's unpack this. Imagine a world where the very stuff of reality, everything we usually call particles, energy, forces, is actually, well, just a different name for structured motion.
It's a pretty radical thought, isn't it?
It really is. So today, our deep dive is exploring exactly that, this framework called motion theory, and how it gives us a completely fresh look at spintronics.
Which many of you will know is already a cutting-edge field.
Yeah, absolutely. And we're drawing our insights here from some really interesting excerpts titled Motion Theory on the New Emergent Technology of Spintronics.
Our mission today really isn't just to explain the theory. It's more about helping you see how changing our basic viewpoint like this could, light up the path for future tech. We're talking everything from the next gadget in your pocket to maybe even bigger ideas like consciousness.
Yeah, it's not just a slightly different angle. It's like putting on totally new glasses.
And what's fascinating here is precisely that lens. It really does help make some incredibly complex ideas feel, well, profoundly clear. You start seeing connections, potential that the standard ways of thinking often miss.
Like seeing the whole pattern, not just the dots.
Kind of like that, yeah. But also realizing the pattern itself is the reality. It's all about these coordinated rhythms.
Okay, so let's start right at the beginning then. Motion theory itself.
Right.
What's the core idea?
Well, at its heart, it proposes that everything, atoms, galaxies, light, even maybe thought, isn't made of tiny bits or, energy packets or forces pulling things around.
Right.
Instead, it suggests everything is fundamentally structured, rhythmic motion.
Okay. That's a big shift from particles and fields.
It's huge. And within this view, all those concepts we're used to, they get redefined in terms of motion. So particles, they become stable looping patterns of motion. Like think of a little whirlpool that holds its shape.
A motion loop.
Yeah. And forces, they're not really pushes or pulls anymore. They're more like sync gradients. Zones where the motion patterns are, let's say, out of step and things shift around to get back into balance, into sync.
Interesting. So what about something like mass?
Mass becomes resistance to changing rhythm. Imagine trying to speed up or slow down a really complex dance versus just a simple beat. The complex one resists change more. It has more mass in this sense. And energy is basically the intensity of that motion, or maybe its potential to disrupt other patterns.
And space and time. Those are fundamental.
Right. And maybe the most mind-bending part. Space isn't seen as an empty box things move in. Space is the motion itself. It's the dynamic stage. And time is just our way of measuring how those motion patterns change, how the rhythms evolve.
Wow, okay. That really turns things inside out. So if an electron, gravity, everything, if it's all just motion behaving differently, does that change how we should even do science? Not just physics, but everything.
I think it has to, doesn't it? It encourages you to look for the underlying rhythms, the oscillations, the waves, instead of just focusing on isolated things we call particles or forces.
Right, like we've been cataloging instruments without listening to the symphony.
That's a great way to put it. It's realizing that these things we've given different names to are maybe just different performances of the same underlying reality. Motion.
That's quite a foundation. And this is where it gets really interesting when we connect it to spintronics.
Exactly.
So for anyone maybe less familiar, spintronics is, it's this advanced field that uses what's called electron spin, usually described as being up or down, like a tiny compass needle.
Right, an intrinsic angular momentum.
Yeah, and they use that spin state to store or send information, sometimes instead of using the electron's charge, sometimes alongside it. You hear about devices like magnetic tunnel junctions, spin valves.
MRAM in computers, for example.
Exactly. All designed to control and read these tiny spin states. And the big promise has always been, faster computers, memory that uses way less power.
And that's where the standard model, it works incredibly well practically, but conceptually. It sometimes feels a bit, fuzzy. Spin is often treated like this mysterious internal property or just like a quantum switch we flip.
A magic toggle?
Kind of, yeah. We know how to use it, but what is it, fundamentally? And motion theory steps in here with a potentially much more intuitive picture. It says spin isn't some property of a particle. It's a looped motion rhythm locked into a stable sync state.
Okay, break that down. A looped motion rhythm.
So think back to the particle as a stable loop. Spin is like a specific way that loop is looping its internal rhythm locked into one of maybe two stable configurations. Spin up and spin down become these two distinct phase-locked rhythm states.
Like two different stable notes or chords?
Sort of, yeah. And what we call magnetic fields, those become large-scale synchronization zones, areas where these rhythms tend to align or interact in predictable ways.
And spin transport, moving spin information. That's not particles physically traveling down a wire. It's the rhythm pattern itself being passed along, redistributed through this synchronized medium.
I love that analogy from the source material we looked at. It says, think of spintronic materials not as pipes for particles, but as musical instruments for structured motion.
That's it. It really reframes it.
So controlling spin is like learning to tune or play these incredibly small rhythm loops inside materials. It suddenly feels less abstract.
It does, doesn't it? Once you make that initial leap, it feels almost mechanical in a rhythmic sense.
Right. Okay, so let's use this lens now. Let's dig into some key spintronic ideas and see how they look different. Spin currents, for instance. Normally you picture electrons flowing, right?
That's the usual mental image, yeah. Even if there's no net charge moving, we often still think of particles flowing somehow.
But motion theory says?
Well, from this perspective, a spin current isn't about electron bodies moving from A to B. It's more like a coordinated shift in the internal motion patterns across the material. Like a wave going through the crowd at a stadium.
Exactly like that. No one actually needs to run across the stadium for the wave to travel. It's just a transfer of state of synchronized action. So a spin current is like a wave of sync passing from one atomic loop's rhythm to the next.
Okay, and that explains something crucial, right? Why you can have spin currents without charge currents.
Precisely. And why you can even have them in materials that don't conduct electricity well, insulators.
Yeah.
Because it's not about moving charge, it's about transmitting a rhythmic pattern, what the source calls sync translation.
That's huge. Because heat generation from electron flow is a massive bottleneck in current tech.
It is. This points towards potentially much, much cooler, more efficient ways to move information.
Okay, what about spin torque? Spin transfer torque. Traditionally, that sounds like a force, right?
Yeah.
A spin current comes in and sort of pushes a magnet's direction over, flips its magnetization.
Yeah, it's often described almost like a tiny shove.
But motion theory sees it differently.
It reframes it quite elegantly, I think. It's not a physical shove, it's rhythmic interference. Imagine you have one stable rhythm going, like the magnetization in one direction. Then you introduce a strong, different rhythm, the spin current.
Okay.
That new rhythm doesn't just push the old one, it interferes with it, destabilizes it. The system can't maintain both, so it flips to the most stable rhythm it can resolve under the new influence. It's like rhythm negotiation at the atomic level.
So less of a push, more of a resonance shift, finding a new stable harmony.
Exactly. A transition driven by rhythmic compatibility, not brute force.
Fascinating. Okay, one more. GMR, giant magnetoresistance. Hugely important discovery. Basis for hard drive read heads for years. Made Spintronics practical. The standard story is resistance changes dramatically depending on whether magnetic layers are aligned or anti-aligned.
Right. High resistance when anti-aligned, low resistance when aligned.
Now, does motion theory explain that?
Again, it maps really cleanly. Those magnetic layers, they're sync fields, regions with dominant rhythmic patterns. When the layers are aligned, the rhythms match. So motion, the flow of rhythmic information passes through smoothly, low resistance.
Makes sense.
But when they're anti-aligned, the rhythms clash. It creates turbulence for the motion trying to pass through, high resistance. So it's not really about electrons scattering off interfaces in the classical sense.
It's about sync compatibility.
Exactly. How well do the rhythms line up? Does the motion flow easily, or does it hit rhythmic friction?
Okay, this paints a very different but surprisingly coherent picture. So let's take the big leap here. What does this all mean? If motion theory is right, or even just useful, Spintronics isn't just about better computers anymore, is it?
It feels much bigger than that.
The source material calls it humanity's first real attempt to control motion rhythms directly. That sounds profound.
It is profound. If we really connect this to the bigger picture, the potential just explodes. Yes, you get the ultra-efficient memory and logic we already talked about. But think beyond that. Like what?
Well, maybe rhythm-based computation. Moving past just binary zeros and ones, using different stable rhythms or combinations of rhythms to represent information. That could lead towards things like emulating how neurons synchronize in the brain for new kinds of AI.
Neural sync emulation.
Wow. Or even, and this is more speculative, of course, devices that operate on principles closer to consciousness, responding to complex patterns of rhythmic loops, not just lines of code.
Okay, that's really pushing the boundary.
It is. But the point is, If spintronics is fundamentally about controlling motion rhythms, then this fusion with motion theory suggests it's not just engineering. It's potentially the start of, as the source says, motion-native technology, building things based on the fundamental reality of motion itself.
So just to sort of wrap our heads around this core insight, spintronics, viewed this way, is essentially rhythm control.
That's the gist of it. It's not some weird quantum footnote. It's maybe our first technology that gets its hands dirty, manipulating these fundamental structured motion loops. Which implies the future of computing might not be just fast or binary.
It's sync modulation, learning to sculpt and shift these rhythms purposefully.
Yeah.
And this raises a really important question, doesn't it? What if the whole future direction of science isn't ultimately about finding smaller particles or unifying forces in the old way, but about understanding and utilizing motion intelligence?
Motion intelligence.
Yeah. And if that's the case, then spintronics, as advanced as it is, might really be just the very beginning of a much, much larger shift in science and technology.
A whole new paradigm based on rhythm and sync. So a final thought for everyone listening. As you go about your day, maybe just consider, how might rethinking reality itself as structured motion change how you look at things, how you solve problems, or even just observe the world humming around you?